You know, there's a photograph I want to tell you about. It was taken on a clear desert night in 1952 on top of Palomar Mountain in Southern California when an astronomer pointed a 4-8-inch telescope at a particular patch of sky and captured the light from thousands of stars on a single glass plate. Now, photographic plates, and this is the wonderful thing about them, they're remarkably stable. You develop them, you store them carefully, and the image they hold lasts for decades. Centuries even. So that 1,952 photographs still exists. You can pull it out of an archive, hold it up to the light, and see exactly what the sky looked like over California 70 years ago. And here's where things get interesting. A few years back, a team of astronomers, led by a researcher named Beatrice Villarroel, decided to do something rather clever. They took those old photographic plates from the 1950s and they compared them point by point, star by star, with modern digital images of the very same patches of sky, the same coordinates, the same depth, the same exposure, everything matched up as carefully as possible. And what they were looking for, what they really wanted to know, was simple. Had anything changed? Now, you might think the answer would be obviously no. The universe is so vast, so ancient, so unimaginably old, that on the time scale of a human lifetime, much less 70 years, almost nothing should change. Stars live for millions, billions, even trillions of years. The light traveling to us has been on its journey for centuries. The thought that something significant could happen in just 7 decades seems, well, almost laughable. But that's not what they found. What they found, and I want you to sit with this for a moment because it really is profoundly strange, was that approximately 100 objects that were clearly visible on the 1,952 plates, objects that looked exactly like ordinary stars, objects that left bright, unmistakable signatures on the photographic emulsion, are now gone. Not dimmer, not moved, not changed, gone. As if someone had reached up into the sky and erased them. So you should be asking yourself the same question those astronomers asked themselves, the question that I, frankly, find utterly captivating. Where did they go? I mean, look, stars are not supposed to do this. Stars are not supposed to just vanish. And here's the critical thing to recognize. When a star dies, when it reaches the end of its life and exhausts its nuclear fuel, it doesn't disappear. It transforms. It becomes something else. Something that we can still see, something that announces its presence to the universe in unmistakable ways. If the star is small to medium-sized, something like our sun, it doesn't go out with a bang. It puffs up into a red giant, sheds its outer layers in a beautiful glowing shell of gas we call a planetary nebula, and what's left behind is a hot, dense core, a white dwarf that continues to glow for billions of years. We can see it. It's there. The star didn't vanish. It just changed form. Okay, but what if the star is much more massive? What if it's, say, 10 or 20 times the mass of our sun? Well, that's when you get a real cosmic spectacle. The star runs out of fuel, the core collapses catastrophically, and the outer layers crash inward at a substantial fraction of the speed of light. They rebound off the dense core in an unimaginable explosion. We call this a supernova. And let me emphasize just how bright these things are. A single supernova for a few weeks can outshine an entire galaxy of hundreds of billions of stars. It's the kind of event that, when it happened in our own galaxy in 1054 AD, was seen and recorded by Chinese astronomers, by Native American observers in what's now New Mexico, by anyone with eyes pointed at the sky. The remnant of that supernova is still expanding today. We call it the Crab Nebula, and you can see it through a backyard telescope. So if one of those stars had gone supernova between 1,952 and now, we would know. Everyone would know. There would be no missing it. And if the star was even more massive, say 25 times the mass of our sun or more, then what's left behind after the supernova explosion is a black hole. Now, Black holes themselves are dark, of course. They're, black, but they're not invisible. A black hole near other stars or other gas will draw matter toward itself, and that matter, as it spirals inward, will heat up to temperatures of millions of degrees, blazing in X-rays and ultraviolet light. We see these things. We have telescopes specifically designed to spot them. A black hole forming nearby would not be a silent event. So we have these vanished stars, 100 or so points of light captured on plates in 1952, gone today. And none of them seem to have left any of the expected signatures behind. No glowing nebula where a star died gracefully, no supernova remnant, no new X-ray source where a black hole might be feeding, just nothing, empty sky. Now, here's where I have to be honest with you, because this is the responsible thing to do when we're talking about science. The first explanation, the boring explanation, the explanation that any careful scientist has to consider first, is that those old photographic plates might have artifacts on them. Maybe a cosmic ray hit the emulsion. Maybe a piece of dust on the lens caused a fake star to appear. Maybe an asteroid happened to pass through the field of view during the exposure. These things happen. They happen all the time. And in fact, when the VASCO team, that's the name of the project, VASCO, which stands for Vanishing and Appearing Sources, during a century of observations, when they went through their initial list of candidates very carefully, most of the suspects turned out to be exactly that: glitches, defects, things that looked like stars but weren't. The list got smaller and smaller as they applied stricter and stricter criteria. But here's the thing. After all the filtering, after throwing out every candidate that could possibly be explained by an artifact, there remained a residual sample, a handful of objects, maybe a dozen, maybe more. Objects that had bright, clear signatures on the 1,952 plates that looked exactly like ordinary stars and that have no detectable counterpart today, even with telescopes orders of magnitude more sensitive than the ones used in 1952. And these are the cases that are difficult to dismiss. These are the cases that keep astronomers up at night, because in a properly functioning universe, ruled by the physical laws we think we understand, this should not be happening. Now, before we go any further, I want to pause and consider something. Something that I find both terrifying and beautiful in equal measure. Because the truth is, the headline I just spent 10 minutes building up to stars are disappearing is actually only half the story. The other half, the half I think is even more remarkable, is hidden in the title of this video. Something is erasing stars from the sky, and it's getting closer to us. What does that mean? What could possibly be coming toward us, and why should you, sitting wherever you're sitting right now, care? Well, let me back up and tell you a different story. A story that begins not in 1952, but more than 2 centuries earlier, on a cold night in England, when a man named William Herschel pointed his homemade telescope at the Milky Way and noticed something deeply strange. Herschel, was a remarkable character. He started his career as a musician, a composer, and oboist, actually, with a respectable career in Bath, but he became fascinated with astronomy in middle age and ended up discovering the planet Uranus, which earned him a royal appointment and changed the course of his life. He built telescopes larger than anyone had built before. Some of them were monstrosities, 40 feet long, requiring teams of assistants to operate, and night after night, he and his sister Caroline mapped the heavens, cataloging stars and nebula and trying to understand the structure of our galaxy. Now, when Herschel looked at the band of light we call the Milky Way, and I'm sure you've seen pictures of it, that gorgeous river of stars stretching across a truly dark sky, he noticed that it wasn't smooth. It was lumpy. It had bright regions where stars seemed to crowd together, and it had dark regions where stars seemed to be entirely absent. In some places, against the otherwise bright background of the galactic disk, there were yawning gaps, holes, patches of utter blackness, as if someone had taken a punch and removed the stars from those regions. Herschel had a theory about this, and it's worth pausing to appreciate how sensible his theory was, even though it turned out to be completely wrong. He thought these dark patches were exactly what they appeared to be, holes, actual gaps in the distribution of stars. He famously wrote in his notebook, looking at one particularly dark region, "Surely this is a hole in the heavens." And I love that phrase, "a hole in the heavens," because it captures something so human, so intuitive about how we interpret what we see. If you see darkness where there should be stars, the natural conclusion is that there are no stars there. But Herschel was wrong. And he was wrong in a way that took more than 100 years to fully understand. Because you see, those dark patches aren't holes at all. They're not absences. They're not gaps in the distribution of stars. They are, in fact, the exact opposite of an absence. They are the presence of something, something dense, something cold, something that lies between us and the stars beyond, and that blocks the light from those stars completely. What Herschel was seeing, though he couldn't have known it, were dark nebulae. Vast clouds of interstellar dust and gas drifting through the galaxy, dense enough and large enough to absorb the light of every star behind them. Now you might wonder, what do we mean by dust in space? When I say dust, I don't want you to picture the stuff on your bookshelf. Interstellar dust is something a little different. It's made of tiny grains, much smaller than a grain of sand, much smaller even than the dust mites in your carpet. We're talking about particles, maybe a few hundred molecules across, made of carbon, of silicates, of frozen water, and various organic compounds. Each individual grain is essentially invisible. But when you have enough of them, when you have a cloud that's many light years across, containing trillions upon trillions of these particles, they become an effective wall. Light from behind the cloud hits the grains, gets absorbed, scattered, redirected, and what we see on the other side is darkness. The discovery of this fact, by the way, was one of the great surprises of 20th century astronomy. There had been hints earlier, scattered observations that didn't quite add up. But it wasn't until astronomers like Robert Trumpler, working in the 1930s, started carefully measuring the brightness and distance of star clusters that the picture became clear. Trumpler noticed that distant star clusters appeared systematically dimmer than they should have been based on their actual size. Something was sapping the light as it traveled across space. And the more space the light traveled through, the dimmer it became. There was quite literally stuff in the way. This realization changed astronomy. It meant that what we see in the sky is not a clean, unobstructed view of the universe. It means we're peering through a kind of cosmic fog, thicker in some directions, thinner in others. And in the densest patches, the fog becomes opaque. The light from beyond cannot penetrate. Stars that are physically out there, perfectly normal, and presumably shining away, simply cannot be seen from where we are. So here's a question that I want you to hold on to, because it's going to matter as we go forward. If interstellar dust can hide stars from us, can it also, do this in reverse? Can clouds of dust move? Can they drift? Can they shift across the sky over time, revealing stars that were hidden and hiding stars that were once visible? Could that be what's happening with the vanishing stars? Is some dust cloud somewhere out there in our galaxy moving in such a way that it's now blocking the light of stars that used to be in plain view? This is a perfectly reasonable hypothesis. And to assess it, we need to think a little bit about what's actually out there. What lies between the stars in our part of the galaxy? Is it empty, or is it filled with stuff? And if it's filled with stuff, what kind of stuff, and how is it arranged? The answer, it turns out, is that the space between the stars is anything but empty. The space between the stars is a vast, complex, evolving ecosystem of gas and dust and magnetic fields and high-energy particles, all of it churning and flowing on enormous scales. We call this collectively the interstellar medium. And the interstellar medium is structured in a way that you would find, I think, quite surprising. Right around our solar system, for a sphere extending about 1,000 light years in every direction, the interstellar medium is unusually thin, diffuse, almost, and I emphasize almost, empty. We call this region the local bubble. And the reason it's a bubble, the reason this region of space is so much less dense than the average patch of the galaxy, is because something blew it clear. Astronomers have pieced together a story that goes something like this. About 14 million years ago, in a region of the galaxy not far from where the sun is now, a series of massive stars reached the ends of their lives and exploded as supernovae. Not just one, but maybe a dozen or more, going off over a period of several million years. The shock waves from these explosions plowed through the surrounding interstellar medium, sweeping the gas and dust outward in a great expanding shell. The inside of that shell got cleared out. The gas became hot and thin and tenuous, and our sun, drifting along its orbit around the galactic center, happened to wander into that cleared out region a few million years later. We're living, right now, inside the cavity carved out by ancient stellar explosions, the local bubble, a hollow in the galaxy's foggy interior. And it's that hollow, that relative emptiness of our cosmic neighborhood, that allows us to see so clearly out into the wider universe. If the sun were located in a denser part of the galaxy, our view of the cosmos would be obscured. We might not even know that other galaxies existed. Now, the local bubble isn't perfectly empty. There's still some gas in here, some dust, just a lot less of it than there would be outside. And there are scattered within the bubble denser pockets, little wisps and tendrils of interstellar material. Some of these are large enough to have their own names. There's the local interstellar cloud, sometimes called the local fluff, and I just love that name. The local fluff, it sounds like something from a children's book, which is a small, wispy cloud of slightly denser gas, about 30 light years across. Our solar system happens to be inside the local fluff. We entered it sometime in the last 100,000 years or so, and we'll probably exit it within the next 10,000 to 20,000 years. There are other clouds nearby. There's the G cloud, sitting just beyond the edge of the local fluff in the direction of the constellation Centaurus. There's the blue cloud, the aqua cloud, the airy cloud. There's a whole catalog of these little wisps, each one a slightly denser pocket of interstellar material, all of them drifting through space with their own velocities, their own trajectories. And here is where the story I'm telling you starts to converge. Because the sun is moving, we're not stationary. We're orbiting the center of the Milky Way at about 230 kilometers per second, which is about 514,000 miles per hour. And within that orbit, we have our own peculiar motion through the local environment. We're heading, roughly speaking, in the direction of the constellation Hercules. And as we move, we're not just passing through empty space, we're passing through clouds. We've been in the local fluff for a while now, and we're heading directly into the G cloud. So here's the wonderful kind of unsettling thought. Something is, in fact, coming toward us, or, to be more precise, we're moving toward it. We're going to enter the G cloud sometime in the next few thousand years, maybe sooner, maybe later. It depends on exactly where the boundary is and our exact velocity, but it's going to happen. What will that be like? Well, the G cloud is denser than the local fluff. It's denser than the surrounding bubble. When we enter it, the heliosphere, that bubble of solar wind and magnetic field that surrounds our solar system and protects us from interstellar radiation, is going to get compressed. The boundary that currently extends about 100 astronomical units beyond the Sun, well past Pluto, that boundary is going to move inward. Cosmic rays are going to penetrate more deeply into our region of space. The Earth's atmosphere is going to be exposed to higher levels of high-energy particles than it has been in recent geological history. Now, I want to be clear, because I don't want anyone panicking. This is not, an immediate threat. We're not going to wake up tomorrow and find ourselves engulfed in a deadly cloud. The transition will be slow, gradual, taking place over thousands of years. And the G cloud, while denser than what we're in now, is still much less dense than what you'd find in really thick interstellar clouds elsewhere in the galaxy. Life on Earth has been through similar transitions in the past. We've been in and out of denser clouds many times during the Sun's 4.5 billion year history. Each transition probably changed conditions on Earth in subtle ways, changing the rate of cosmic ray bombardment, perhaps affecting cloud formation, perhaps influencing climate. Some researchers have even speculated that passages through dense interstellar clouds might be connected to ice ages or mass extinctions. But on the timescale of a human life, even on the timescale of all human history, the effects are negligible. But here's the deeper question. The question that brings us back to the mystery of the vanishing stars. Could the things happening in our local cosmic environment, the motion of clouds, the shifting of dust, be enough to actually erase stars from the sky? Could a denser pocket of interstellar material moving across our line of sight to a distant star be enough to make that star vanish from view? Well, here's where I have to give you the honest answer, which is probably not, or at least not in the way we're discussing. The stars that vanished in the Vasco survey weren't slowly fading. They were there in 1952 with their full brightness, and now they're gone. A drifting dust cloud would, generally speaking, cause a gradual dimming, not a complete disappearance. And the timescales for interstellar clouds to move appreciably across our field of view are, in most cases, much longer than 70 years. So dust clouds, the ordinary interstellar medium, probably can't account for the missing stars, which means, and this is where things get really interesting, we need to look elsewhere. We need to consider possibilities that go beyond the standard cosmic fog. We need to ask whether there might be other things out there in the galaxy, things that don't shine, things that don't show up in our normal surveys, things that could move quickly enough or that could intervene strangely enough to make a star simply disappear. And this is where modern astrophysics has been generating some, I have to say, deeply unsettling ideas. Ideas about what might be lurking in the dark spaces between the stars. Ideas about the nature of the universe at scales we have barely begun to explore. Have you ever heard, for instance, of failed supernovae? The standard picture, the one I outlined a few minutes ago, says that when a massive star runs out of fuel and its core collapses, the result is either a neutron star or a black hole, with a brilliant supernova explosion announcing the event to the universe. But what if that's not always the case? What if, sometimes, the collapse happens so quickly, so completely, that the outer layers of the star never get the chance to bounce and explode? What if, sometimes, a massive star just falls in on itself, quietly, without fanfare? This is no longer a hypothetical question. Astronomers have reported observations of a star in a nearby galaxy, the spiral galaxy NGC 6946, sometimes nicknamed the fireworks galaxy because it produces so many supernovae that it appears to have done exactly this. The star, designated N6946 was a massive red supergiant, about 25 times the mass of our Sun, and astronomers had been monitoring it for years. In 2009, it briefly flared in brightness, glowing brighter than normal for several months, and then it disappeared. Not just dimmed, disappeared. Subsequent observations with the Hubble Space Telescope and other facilities failed to find it. The star was just gone. The interpretation that astronomers have settled on, tentatively, is that we were watching a failed supernova. The core of the star collapsed directly into a black hole without the usual explosion. A small burst of energy escaped during the collapse. That's the brief flaring, but most of the star's matter fell straight into the new black hole. The result is a black hole sitting where a star used to be, surrounded by no expanding remnant, accompanied by no supernova fireworks. To the eye and to almost any of our telescopes, the star simply vanished. Now, here's why this matters for the missing stars in the Vasco survey. If failed supernovae are a real phenomenon, and the evidence is growing that they are, then we expect a significant fraction of massive stars to end their lives this way. Maybe 10%, maybe more. And every one of those stars will, in essence, disappear from our view, leaving behind a black hole and not much else. If you were running a survey of the sky, comparing images from decades apart, you'd see these stars vanish, just like the Vasco team did. So that might be part of the answer. Some of the vanished stars in the survey might be failed supernovae, massive stars that collapse into black holes without putting on a show. And the truly fantastic thing about this, the thing that makes me genuinely excited as a physicist, is that it means we have a new way of finding black holes. Not by detecting the X-rays they emit when they accrete matter, but by watching for the absence of stars that used to be there, a kind of negative space astronomy, looking for things by looking for what's not there. But, and you knew there was a but coming, not all the vanished stars in the Vasco survey can be explained this way. Failed supernovae should only happen to the most massive stars, and those are rare. The candidates in the Vasco survey include objects that appear too faint to be massive stars, things that look like more ordinary, more sun-like objects. And ordinary, sun-like stars are not supposed to collapse into black holes. The physics just doesn't allow it. They simply don't have enough mass to overcome the quantum mechanical pressures that would, keep them stable as white dwarfs or neutron stars. So if some of these vanished objects aren't massive stars undergoing failed supernovae, and if they're not dust clouds passing in front of them, what are they? What could possibly explain a sun-like star disappearing without a trace, without a remnant, without a single photon left behind to tell the story? And this is the question that I find truly thrilling, because to answer it, we may need to consider possibilities that take us into the deepest, most speculative corners of modern physics. We may need to talk about objects that have been theorized but never confirmed, about forms of matter that we suspect exist but have never directly detected, about possibilities that frankly sound more like science fiction than science fact, but that careful researchers are now treating with deadly seriousness. We may need to talk about primordial black holes, about dark stars, about the possibility that the dark matter that makes up most of the gravitational mass of our galaxy is not, as we've long assumed, some kind of exotic subatomic particle, but is instead made of much more ordinary sounding objects, objects that could, in principle, drift through space, occasionally passing in front of or even consuming the stars we observe. We may need to talk about things that, by their very nature, we can never see directly, things that betray their presence only through their gravity, their absence, the holes they leave behind in our view of the cosmos. And we may need to talk about the unsettling possibility that some of these things are not safely far away, off in the distant reaches of the galaxy, where they can't affect us. Some of them may be quite close. They may be in our cosmic neighborhood. They may, in fact, be passing through the local bubble right now. They may, in some sense that I'll explain in just a moment, be heading our way. So here's where I want to leave you at the end of this first part of our journey. with a sense of the puzzle we're trying to solve, with a feeling for the strangeness of it, and with a hint of what's to come. Because in part 2, I want to take you deeper into this mystery. I want to talk about a class of objects that physicists have theorized for half a century. Objects that could be lurking in the dark spaces of our galaxy by the millions. Objects that, under the right circumstances, could move through space in ways that would make stars vanish before our eyes. I want to introduce you to a kind of cosmic detective work that combines gravitational lensing, microwave background observations, and high-precision astrometry to hunt for things that should be invisible. And I want to tell you about a discovery made just within the last few years that has raised the possibility that we are not, in fact, alone in the local bubble, that we share this little cleared-out region of the galaxy with companions we cannot directly see, companions that move on their own trajectories, companions that may, on a long enough timescale, drift through our region of space. Something, you see, really is erasing stars from the sky. And there is, I think, good reason to believe that the agents of this erasure are not always far away. They may be much closer than we'd like to think. And one of them, if our calculations are right, and they may not be maybe slowly, silently, inexorably heading this way. So when you look up at the stars tonight, I want you to consider the possibility that the sky you see is not the same sky that your grandparents saw, and it is not the same sky that your grandchildren will see. The universe, even on a human time scale, is in motion. Things are appearing, things are disappearing, and the cosmic dark, as we will discover, may not be quite as empty as it appears. So we'd arrived at this rather unsettling point where ordinary explanations, dust clouds drifting across our line of sight, failed supernovae quietly swallowing massive stars, well, they could account for some of the vanished objects in the VASCO survey, but not all of them. And the ones they couldn't account for, the residual mystery, are the cases that should keep us up at night. Because the implication, the thing that the data seems to be telling us, is that there might be other things out there, things we've theorized about for decades, but never directly observed, things that could, in principle, hide stars or even consume them and leave us scratching our heads at empty patches of sky. So I want to take you now into one of the most beautiful and, frankly, one of the most counterintuitive ideas in modern physics. An idea that goes back to the 1960s, that has been worked on by some of the most brilliant theoretical physicists of our time, including Stephen Hawking himself, and that has, in the last few years, undergone something of a renaissance. I'm talking about primordial black holes. Now, when most people think about black holes, and you've probably heard about black holes plenty by now, they're everywhere in popular science, they think of them as the end states of massive stars. A star much heavier than our sun runs out of fuel, collapses, explodes as a supernova, and leaves behind a black hole. That's the standard story, and it's a correct story as far as it goes. Those kinds of black holes, the stellar mass black holes, definitely exist. We've observed them in binary star systems for decades. We've directly imaged them with the Event Horizon Telescope. We've heard their collisions through gravitational waves. They are, in this sense, well-established residents of our universe. But here's the thing. Stellar collapse is just one way to make a black hole. And it turns out that in the very earliest moments of the universe, in conditions so extreme that they make a supernova look like a candle, there may have been an entirely different mechanism for forming black holes. A mechanism that operated long before the first stars existed. A mechanism that could produce black holes of any mass, including masses that are completely impossible for stellar collapse black holes to have. Let me back up and explain what I mean. We have very good evidence that the universe began about 13.8 billion years ago in a state of extraordinary density and temperature. The Big Bang, is the standard term for it. though it's a somewhat misleading name because it wasn't really a bang in the conventional sense. It was more like an expansion of space itself, starting from a state where everything was packed together in a way that defies our normal intuitions. And in those first fractions of a second, the universe was so dense and so hot that the physics was nothing like what we experience today. Quantum effects dominated. Pressure and temperature were unimaginable. Energy density was such that in places, the conditions for gravitational collapse could occur on absolutely tiny scales. Here's the idea, in essence. The early universe wasn't perfectly uniform. There were tiny fluctuations in density, ripples in the primordial soup, regions that were slightly more dense than their surroundings. Most of these fluctuations were small. They grew over billions of years, eventually seeding the structure of galaxies and clusters and the cosmic web. But occasionally, by sheer statistical chance, a fluctuation might have been large enough in a small enough region to trigger immediate gravitational collapse. That region of unusually dense primordial matter would simply fall in on itself right there in the first second after the Big Bang and form a black hole. Now, the wonderful thing about this mechanism and the reason it's so different from stellar collapse is that it doesn't require the black hole to be very massive. A stellar collapse black hole has to be at least about 3 times the mass of our Sun, because below that mass, the quantum mechanical pressures inside a neutron star are strong enough to prevent collapse. But primordial black holes have no such restriction. They could be as small as an asteroid or as massive as a galaxy. They could have any mass at all, depending on the exact size of the density fluctuation that gave birth to them. And here's where it gets really interesting. If primordial black holes formed in the early universe, and if they had the right range of masses, they could still be around today. They wouldn't have evaporated because Hawking radiation, the slow leakage of energy from black holes that Stephen Hawking famously discovered, only matters significantly for very small black holes. A primordial black hole more massive than about 1 trillion kilograms would, survive the entire age of the universe without losing a meaningful fraction of its mass. It would just keep doing what black holes do, sitting there, lurking, pulling on things gravitationally. And here's the kicker. Here's the part that has the astrophysics community in such a state of intense interest right now. Primordial black holes, if they exist in sufficient numbers, could account for some or all of the dark matter in our galaxy. Dark matter, as you may know, is the invisible stuff that makes up about 85% of all the matter in the universe. We know it's there because we can see its gravitational effects on galaxies, on the rotation curves of stars, on the way light bends around clusters, but we have never directly detected what it actually is. For decades, the leading hypothesis has been that dark matter is some kind of weakly interacting particle, something exotic from particle physics. But despite 40 years of searching with increasingly sensitive detectors, no such particle has ever been found. And so, in recent years, the idea that dark matter might be made of primordial black holes has come roaring back. Maybe what we call dark matter isn't some mysterious new particle at all. Maybe it's just a vast population of small black holes formed in the first second of the universe, scattered throughout the galaxy, invisible because they're black, but present in enormous numbers. Now, take a moment with this. Think about what it would mean if dark matter is primordial black holes. Then our galaxy isn't just a collection of stars and gas. It's also a collection of black holes, vast numbers of them, drifting between the stars, moving on their own orbits around the galactic center, mostly small, perhaps the mass of a planet or a small moon, but black holes nonetheless. The space between the stars isn't empty. It's, populated. It's populated by objects that we cannot see directly, that interact with normal matter only through gravity, and that on rare occasions must pass close to the stars and gas that we can see. You can probably see where this is going. If primordial black holes exist, and if they make up some significant fraction of the dark matter, then occasionally, not often, but occasionally one of them is going to pass directly in front of or even into a star. And what would that look like? Well, the answer depends on the mass and trajectory of the black hole and the size and density of the star. But the possibilities are genuinely strange. If the black hole is small and passes through the outer layers of a star quickly, it might leave the star largely intact, just punching through with relatively little disturbance. But if the black hole is more massive, or if it gets captured by the star's gravity, it might settle into the core. It might begin to slowly consume the star from the inside out. The star would continue to shine for a while, but it would gradually lose mass, becoming dimmer and dimmer until eventually the entire star would be drawn into the black hole. And then, well, what would we see from Earth? We'd see a star that fades and then disappears without any of the usual signatures of stellar death. No supernova, no planetary nebula, no expanding cloud of debris, just a star, there one decade, gone the next. Does that sound familiar? Does that sound perhaps like exactly the kind of thing that Vasco has been finding? Now look, I want to be careful here. The hypothesis that some of the Vasco objects are stars being consumed by primordial black holes is, highly speculative. There are many things that have to be true for this picture to work out, and we don't yet have direct evidence that any of those things are true. But the possibility is real enough, plausible enough, that astrophysicists are actively investigating it. And that in itself is remarkable. But I want to take this further, because there's another aspect to the primordial black hole story that I find genuinely thrilling. And that aspect is that if these things exist, they should leave detectable fingerprints even when they're not consuming entire stars. They should produce subtler effects. Effects that we have in the last few years started to look for in earnest. The most beautiful of these effects is something called gravitational microlensing. Now, the basic idea behind gravitational lensing comes straight out of Einstein's general theory of relativity. Mass curves space, and light follows the curvature of space. So when light from a distant star passes near a massive object on its way to us, the light gets bent. It can be bent so much that the distant star appears to be in a different location than it actually is, or split into multiple images, or magnified, or distorted in ways that are predictable from Einstein's equations. For massive lenses, like galaxies, the effect is dramatic. You can see beautiful arcs and rings in the sky, formed by light bending around foreground galaxies. But for smaller lenses, like individual stars or planet mass objects, the effect is more subtle. The angular displacement is too small to resolve. What you see instead is a temporary brightening. The distant star appears to get brighter for a few hours, or a few days, or a few weeks, depending on the mass of the lens and how perfectly it passes in front of the source, and then it fades back to normal. This is microlensing. And it's a remarkable tool because it lets us detect objects that we can't see directly. A primordial black hole drifting through space with no light of its own would still produce a microlensing signature when it happened to pass in front of a distant star. The signature would be a characteristic light curve, a smooth rise and fall in the brightness of the background star, with a shape that depends in a precise way on the mass of the lens. For the past several decades, astronomers have been running large-scale microlensing surveys, monitoring hundreds of millions of stars in the central regions of our galaxy and in the Magellanic Clouds, looking for these telltale brightenings. And they found them, lots of them. The vast majority can be attributed to known objects, ordinary stars, brown dwarfs, planets. But there's a residue a small fraction of microlensing events that don't fit the expected pattern, events that suggest the presence of compact dark objects with masses in a particular range. And some researchers are now arguing that this residue could be the signature of primordial black holes. Now, the case is not airtight. There are alternative explanations. The masses of the candidate objects, the rates at which they're detected, the spatial distribution, all of these have to be consistent with what we'd expect from a primordial black hole population, and matching all the constraints is, a genuinely difficult exercise. But the door is open. The hypothesis is not refuted. And in the next decade, as new telescopes come online, particularly the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope, we expect to dramatically increase our ability to detect microlensing events and constrain the primordial black hole population. So here's where we are. We have a missing stars problem. We have a viable hypothesis, primordial black holes that could explain at least some of the missing stars. We have microlensing surveys that have found tentative evidence for a population of compact dark objects in our galaxy. And we have new instruments coming online that will let us test this idea much more rigorously in the years ahead. But I promised in the title of this video that something was getting closer to us, and it's time to make good on that promise. Because the story I've been telling about primordial black holes and the populations of invisible objects in our galaxy has a local dimension, a neighborhood dimension, and that's where it gets, somewhat personal. I want to introduce you to a discovery made very recently that has astronomers and astrophysicists thinking quite seriously about the contents of our own backyard, about the immediate cosmic environment of our solar system, about what's out there, what we can see, and what we cannot. The discovery has to do with an unusual phenomenon called a free-floating black hole. Now, traditionally, when astronomers have wanted to find black holes, they've looked for them in binary systems, pairs of objects where a black hole is orbiting with a normal star. And the gravity of the black hole pulls material off the star, and that material gets superheated as it spirals into the black hole, and it produces X-rays that we can detect. This is how all of the stellar mass black holes in our galaxy have traditionally been found, through their interaction with companion stars. But there's a problem with this approach. Most black holes, if they exist in the numbers that we expect from stellar evolution, are not in binary systems. They're alone, drifting through space by themselves, not accreting any matter, not producing any X-rays, not announcing their presence in any obvious way. These are the free-floating black holes. And by some estimates, there should be 100 million of them in our galaxy. 100 million silent black holes drifting through interstellar space, invisible to all of our traditional black hole detection techniques. How would we find them? Well, by microlensing, as I mentioned, by watching for the characteristic brightening of background stars when a free-floating black hole passes in front. And in 2022, after years of careful work, 2 independent teams of astronomers announced what may be the very first confirmed detection of a free-floating stellar mass black hole using exactly this technique. It was found in a microlensing event called MOA 2011BLG 1910GLE 2011BLG 0462. And I know that's a mouthful, but those names are catalog designations indicating when and where the event was discovered. The event itself was a brightening of a distant star observed back in 2011 that took longer to play out than typical microlensing events and showed subtle astrometric effects, meaning the position of the background star shifted slightly during the event as expected for an unusually massive lens. When the dust settled, when the data was carefully analyzed, the answer that came out was, frankly stunning. The lens appears to be a black hole with a mass of about 7 times the mass of our sun, located about 5,000 light years away. And here's the part I want you to pay attention to. It is moving rapidly through space. Its peculiar velocity, the component of its motion that's not due to general galactic rotation, is something like 45 kilometers per second. That's much faster than a typical star in the galaxy. It's moving like something that got a kick, like something that was launched from its place of origin by a violent event, almost certainly the supernova explosion that gave birth to it, which can impart enormous velocity boosts to the compact objects that remain. So here we have it. The first confirmed, isolated, free-floating black hole, a real, observed, characterized, stellar mass black hole drifting through space by itself with no companion star, no X-ray emission, nothing to give it away except the tiny gravitational signature it imprinted on the light of a distant background star. This was a kind of triumph. It proved that the technique works. It proved that free-floating black holes are real. And it raised, the obvious follow-up question. If we found one, how many more are there and where are they? And this is the question that connects everything we've been talking about. Because if free-floating black holes exist in the numbers that we expect 100 million in our galaxy, then they are everywhere. They are scattered throughout the disk of the Milky Way. They are passing close to other stars all the time. They are, in some statistical sense, present in our cosmic neighborhood. How close could one be? Well, that depends on how many there are and how they're distributed. If we take the rough estimate of 100 million free-floating black holes in our galaxy and we distribute them more or less in the same way that stars are distributed, then we expect a density of, something like 1 free-floating black hole per cubic kiloparsec in our local region. A cubic kiloparsec, by the way, is a volume about 3,300 light years on a side. So 1 black hole, somewhere in that volume, the nearest free-floating black hole, statistically, might be on the order of 1,000 light years away. Maybe closer, maybe farther, but somewhere in that ballpark. And that's not, a comfortable distance, but it's also not an alarming one. 1,000 light years is well outside the radius of influence of even the most extreme objects. A free-floating black hole at that distance would have no effect whatsoever on our solar system. It would just be sitting there, drifting along, occasionally bending the light of stars behind it. But here's where the story takes another turn. Because in the last few years, astronomers have begun to find evidence for objects much closer than that. Objects in the immediate vicinity of our solar system. Objects that might be even stranger than ordinary free-floating black holes. And to tell you about these, I need to introduce you to a class of stars called the high-velocity stars. These are stars that, for reasons that aren't always obvious, are moving through the galaxy at speeds far exceeding what's typical. They're, hypervelocity travelers. And in some cases, when we trace back their trajectories, we find that they appear to have been ejected from binary systems where their companion was a compact object, a neutron star or a black hole. The companion stays behind, alone, while the visible star is flung outward at high speed. There's a particularly intriguing pair of objects in the constellation Monoceros, designated V723 Mon, where a giant star appears to be orbiting an unseen companion. And the unseen companion, based on the mass needed to produce the observed motion of the visible star, appears to be approximately 3 solar masses. That's right at the boundary between what could be a heavy neutron star and what must be a black hole. And it's only about 1,500 light years away from us. That's relatively close in galactic terms, though still very far from the solar system. But these objects, even when they're close in galactic terms, are still far away in human terms. And the story I want to tell you, the story that connects to the idea of something erasing stars and getting closer to us, requires me to take you into even more speculative territory. Territory that, I want to be honest, is genuinely speculative. Not refuted, not impossible, but unconfirmed. What if there are primordial black holes drifting through our solar system right now? I know. It sounds absurd. It sounds like the kind of thing that you'd read about in a tabloid. But it's actually been the subject of legitimate scientific papers in recent years. And the basic argument goes like this. If a significant fraction of the dark matter in our galaxy is made of primordial black holes with planetary or asteroidal masses, say, around the mass of a small moon, or even smaller, then there should be billions of them in the volume of our local galactic neighborhood. They should be drifting on their own orbits, with their own velocities, occasionally passing through regions of space that include our solar system. In fact, some researchers have estimated that on average, a primordial black hole with a mass of about 1/10 of an Earth mass might pass through our solar system once every few thousand years. Now, most of these passes would be far from the sun, way out in the Oort cloud or the Kuiper belt. We wouldn't notice them. They'd zip through, gravitationally perturb a few distant comets, and zip out the other side. But occasionally, and I really do mean occasionally, on geological timescales, one of them might pass close enough to the inner solar system to have a more noticeable effect. Has this happened? Could it happen? Could it have already happened in the past? And might that explain certain features of our solar system that are otherwise puzzling? This is the question that some researchers are now seriously asking. There have been papers suggesting that the orbits of certain trans-Neptunian objects, the icy bodies out beyond the orbit of Neptune, show signatures that might be explained by gravitational perturbations from a passing massive object. Some have speculated about a hypothetical Planet 9. Others have suggested that a primordial black hole could be a candidate for whatever's perturbing these orbits. I want to emphasize again that this is genuinely speculative. We have no confirmed evidence that a primordial black hole has ever passed through our solar system. The Planet 9 hypothesis itself remains controversial, and even if Planet 9 exists, it's more likely to be a conventional planet than a black hole. But the possibility is on the table. It's a topic of legitimate scientific discussion, and it raises questions that I think are quite profound. Because you see, if there are countless invisible black holes drifting through the galaxy, then we are not alone in the local bubble. We share this space with companions we cannot directly see. They are out there somewhere, moving on their own trajectories, indifferent to our presence. They are the silent population of the cosmos. And one of them, statistically speaking, eventually will pass through our region of space. When? Well, that's the question that no one can answer with certainty. Maybe it's already happened in the distant past and we've never noticed. Maybe it'll happen far in the future, long after we're gone. Or maybe, and this is the thought that I find quite arresting, maybe it's happening right now. Maybe there is a primordial black hole or some other compact dark object currently within a few light years of our solar system drifting toward us on a trajectory that over millennia will bring it closer and closer to our cosmic neighborhood. We wouldn't see it. We couldn't see it. It would announce its presence only through subtle gravitational effects, through microlensing events in front of distant stars, through perturbations of comets in the Oort cloud, through changes in the dynamics of our local interstellar environment. And here's the thing. Here's the thought that really, brings this all together. If such an object is approaching us, it might also occasionally pass in front of distant stars. It might, on its journey through space, intervene in the light path between us and stars far across the galaxy. And those stars briefly would disappear from our view, erased, hidden by something we cannot see. Could this be what Vasco is detecting? Could some of those missing stars be the gravitational shadows of compact dark objects drifting through our cosmic neighborhood, hiding stars from us as they pass? Probably not all of them. As I said, the leading explanations remain things like failed supernovae and observational artifacts. But the possibility, that a fraction of the events might be due to interactions with primordial black holes or other dark compact objects, that possibility is no longer something we can dismiss out of hand. It's a possibility we have to consider, and it's one that in the coming years we are going to investigate with increasingly powerful tools. But I want to leave you now with one more thought before we move into part 3. Because I've been telling you a story that's almost entirely framed by, conventional physics. Black holes, dust clouds, ordinary objects behaving in ordinary ways. And that story has taken us into territory that's genuinely strange, genuinely surprising, genuinely cosmic. What if, however, conventional physics isn't the whole story? What if there are objects out there that we haven't even theorized yet? What if the universe is even stranger than we imagine? Some researchers have begun to wonder whether the missing stars might be evidence of something even more exotic. Boson stars, for instance, hypothetical objects made of bosonic dark matter, which could mimic the gravitational effects of black holes without being black holes. Mirror matter, an entire shadow universe of particles that interact with ours only through gravity. Vacuum decay regions, where the fabric of space-time itself has shifted into a different stable state. And on the wildest fringes, there are those who have speculated about Dyson spheres, technological structures built by advanced civilizations to harvest the energy of their stars, structures that would, by definition, cause those stars to disappear from our view. Most of these explanations are frankly far-fetched. Most are, almost certainly wrong, but the fact that careful scientists are willing to entertain them, even as long-shot hypotheses, tells you something about the state of the puzzle. We genuinely do not know what's making those stars disappear. And the answers, when they come, may force us to revise our understanding of the cosmos in ways that we cannot yet anticipate. So here we are, at the end of part 2. We've gone from a simple observation stars on photographic plates that aren't there anymore to a sweeping vision of a galaxy populated by invisible objects. Black holes drifting silently between the stars. Dark matter in forms we have not yet imagined. And the possibility that some of these invisible companions are not safely far away, but are in fact in our backyard, in our cosmic neighborhood, perhaps even moving in our direction. In part 3, I want to bring this story home. I want to talk about what all this means for us, for our place in the universe, for the future of our solar system. I want to talk about what we can actually see today, because some of the most recent observations have revealed structures in our local cosmic environment that are genuinely surprising, even to professional astronomers. I want to talk about the journey our solar system is currently on and the cosmic features we are about to encounter. And I want to bring you, at the end, to the profound philosophical question that the disappearing stars force us to ask. What does it mean to live in a universe where things can simply vanish and where the dark, far from being empty, is full of, presences we can barely begin to perceive? So when you go out tonight, when you look up at the stars, I want you to think about something. The dark patches in the sky, the places between the stars, are not empty. They're populated by gas, by dust, by perhaps 100 million silent black holes, by who knows what else. The cosmos is teeming with things we cannot see. And one of those things, in the great cosmic dance, may be coming our way. So we'd arrived at this point where the universe, viewed honestly, is not the clean, orderly thing we might have hoped for. It is, instead, a place where things can disappear without warning, where vast populations of invisible objects drift through the dark between the stars, and where our cosmic neighborhood, our little local bubble, our reassuring patch of cleared-out galaxy, turns out to be sharing space with companions we cannot directly perceive. And the question I want to take up now, in this final part of our journey, is what all of this means. What it means for our understanding of the universe. What it means for our place in it. And what it means for the future, both near and distant, of the cosmic neighborhood we call home. But before I get to that, I want to do something that I think will help anchor everything we've been discussing. I want to bring this story back down to earth, quite literally. I want to talk about what we can actually see right now with telescopes that exist today when we look out at our local cosmic environment. Because, some of the most recent observations have revealed structures in our backyard that are genuinely surprising, even to professional astronomers. And these observations are, I think, the missing piece that ties together everything we've been talking about. In 2022, a remarkable paper appeared in the journal Nature. The authors had used data from a European space mission called Gaia, and Gaia, I should mention, is one of the great astronomical instruments of our time. It's a space telescope that has measured the positions, motions, and distances of nearly 2 billion stars in our galaxy with unprecedented precision. The Gaia data is, transformative. It's allowing us to map the Milky Way in a way that was simply impossible just a decade ago. And what the authors of that Nature paper did was combine Gaia data with three-dimensional maps of interstellar dust to reconstruct in detail the structure of the gas and dust within about 1,000 light years of the Sun. What they found was extraordinary. They found that the boundary of the local bubble, that hollow region in the galactic interstellar medium that we discussed back in part 1, is decorated with structure. The walls of the bubble, where the swept up gas and dust has piled up, are not smooth. They're lumpy. They're filamentary. They contain, in fact, the birthplaces of nearly all the young stars that we can see in our local sky. Think about that for a moment. Every nearby star-forming region that we know about, Taurus, Lupus, Ophiuchus, Chamaeleon, Pipe, Corona, Australis, all of these famous regions where new stars are being born right now, they are all sitting on the surface of the local bubble. They're sitting on a single connected structure. They were all formed when the expanding shock waves from those ancient supernovae piled up the local interstellar medium and triggered the gravitational collapse of dense pockets of gas. We are not just inside an empty hollow. We are inside a hollow with a particular history, a particular geometry, and a particular ongoing story. The expanding shell of the local bubble is quite literally the cradle of all the young stars near us. And this discovery, I want to emphasize, is brand new. It was published in 2022. We have only just begun to understand the structure of our local cosmic environment with this level of detail. There are likely going to be more surprises, more structures, more features that we hadn't suspected. And every one of them tells us a bit more about what's happening out there between the stars and the dark spaces of the galaxy. But here's the thing that I find truly fascinating, and that connects directly to our story about disappearing stars. Within the walls of the local bubble, there are structures that we can map. We can trace the densest filaments. We can identify where new stars are forming, but within the cavity itself, within the volume of mostly cleared out space that surrounds the sun, we cannot see everything. There are objects in here drifting through the cavity that produce no light, that don't interact with the residual gas in any obvious way, and that are essentially invisible to all of our current instruments. The interior of the local bubble is, in a real sense, a place of mystery. We know the walls, we know the boundaries, we know our own approximate position within it, but the rest of the interior, the volume between the walls, is mostly unmapped, mostly dark, and mostly, as we've been discussing, potentially populated. Now, I want to push this further because I think this is where the story really starts to get interesting. The sun is not stationary. We talked about this in part 1. We're moving through the local bubble, heading roughly toward the constellation Hercules on a journey that will eventually take us into the G cloud and beyond. But we're also moving up out of the plane of the galaxy, oscillating slowly above and below the central disk of the Milky Way. Our path through the cosmic environment is complex, three-dimensional, and ongoing. And as we move, the sky we see changes, the structures we can observe shift, the objects we share space with change. And on long enough timescales, even the population of stars visible to the naked eye undergoes complete turnover. This is something that I think people don't fully appreciate. The night sky is not eternal. The constellations are not permanent. They are, fleeting arrangements of bright stars that happen to be visible to us at this moment in cosmic history. 100,000 years ago, the night sky would have looked dramatically different. 100,000 years from now, it will look dramatically different again. Some stars will have moved out of our cosmic neighborhood. Some will have died. New stars will have wandered closer. And some, on the timescales we've been discussing, may simply disappear from view, swallowed by black holes, hidden by dust, or vanish by mechanisms we don't yet understand. So when I think about the Vasco discoveries, the stars that disappeared between 1952 and now, I find them, in a strange way, almost reassuring. Reassuring, that is, because they remind us that the universe is dynamic, that change is the rule, not the exception, that the cosmos we inhabit is not a static painting, but a living, evolving system where things happen on every time scale, including our own. Even on the time scale of a single human lifetime, the universe is busy, the universe is changing, things are coming and going, and we are miraculously around to witness some of those changes. But I also find them, somewhat unsettling, because the disappearance of stars without explanation is a sign that there are processes operating in our galaxy that we do not yet fully understand. There are mechanisms at work that we have not yet identified, and the dark spaces of the galaxy, far from being a peaceful emptiness, are alive with activity that we are only beginning to glimpse. So let me come now to the question I've been building toward, the question that the title of this video poses. Is something getting closer to us? And the honest answer, which I want to give you straightforwardly, is probably yes. Probably several things, actually, but not in the way that, a Hollywood movie would have you believe. Not in the way that suggests imminent danger or cosmic catastrophe. Let me list what we know is happening. First, our solar system is moving through the local bubble at about 13 kilometers per second relative to the local interstellar medium. As I mentioned in part 1, we are heading toward and will eventually enter the G cloud, a denser pocket of interstellar gas. That's coming. That's getting closer. It will alter the structure of our heliosphere when we encounter it, change the flux of cosmic rays reaching Earth, possibly even affect the climate in subtle ways. But the time scale is thousands of years, and the effects are, by any reasonable standard, modest. Second, the entire sun is, as we've discussed, drifting on its orbit around the center of the Milky Way, completing one orbit every 225 million years or so. During the course of that orbit, we move through different regions of the galaxy, encountering different interstellar environments, sometimes denser, sometimes thinner. Over geological timescales, the sun has passed through molecular clouds, spiral arms, and various structures, and each passage has potentially altered conditions on Earth. The next major encounter is probably tens of millions of years in the future, but the sun is, in this very broad sense, always on a journey, always moving towards something. Third, and this is the speculative part, the part where I want to be especially careful there is the question of whether any specific compact dark objects are currently approaching our cosmic neighborhood. As I discussed in part 2, the statistical estimates suggest that primordial black holes, if they exist and make up some fraction of the dark matter, should pass through our solar system relatively often on geological timescales. The nearest free-floating stellar mass black hole is, statistically, probably hundreds or thousands of light years away, and is likely moving on its own trajectory with no particular interest in or relevance to us. But here's the thing. Statistics tell us about averages. Statistics don't tell us about individual cases. And there is no fundamental reason why a particular dark object couldn't be, right now, in our specific vicinity, drifting through space in a way that brings it closer to us over millennia. We cannot rule it out. We cannot, with our current instruments, detect such an object directly. We can only infer its presence from indirect signatures, from the gravitational perturbations it might cause, from the microlensing events it might produce, from the patterns in the sky it might disrupt. And this is, the place where the story takes its most uncomfortable turn. Because the universe, in its true nature, is not a place that respects our preferences for predictability. It is a place where things happen on timescales, both short and long, and we, conscious beings on a small planet in a small corner of one ordinary galaxy, are doing our best to understand what's happening, often after the fact. The stars that disappeared between 1952 and now were already gone before we ever pulled out the old plates and compared them. The dark objects that may be drifting through our cosmic neighborhood are already drifting, whether we've found them or not. Reality, as the physicist Richard Feynman once said, is what doesn't go away when you stop believing in it. And the reality of the cosmos is that it is full of things that we cannot see, that don't care whether we see them, and that go about their cosmic business indifferent to our anxieties. Now, I want to be clear about something, because I don't want to give you the wrong impression. The realistic effects of all these processes on a human timescale are essentially zero. The G-cloud encounter will not destroy civilization. Even if a primordial black hole did somehow pass through our solar system, the most likely outcome would be a slight perturbation of some distant comets and nothing more. The probability that any of the disappearing stars in the Vasco survey corresponds to an event affecting our own region of space is, vanishingly small. We are not in danger. The universe is not, plotting against us. But the deeper truth, the truth that I think is genuinely worth contemplating, is that we live in a much more interesting universe than we usually realize. The universe of our daily experience is a quiet, gentle, stable place. The sky is blue. The sun rises and sets. The stars come out at night, more or less the same arrangement we saw last year. The cosmos seems static and reliable. But behind that comfortable facade, the actual universe is busy. It is dynamic. It is filled with processes operating on every conceivable scale, from the quantum to the cosmic, from the femtosecond to the eon. And some of those processes occasionally intersect with what we can observe. Stars vanish, black holes drift, clouds shift. The cosmos shows us every now and then a glimpse of its underlying restlessness. And I think that's a remarkable thing to know about. Not a frightening thing, not a depressing thing, but a remarkable thing, because it expands our sense of what's out there. It tells us that the universe is not the simple place we sometimes assume it to be. It tells us that there are mysteries right in our own cosmic backyard that we have only just begun to investigate. And it tells us that as our instruments improve, as our methods get more sophisticated, as our patience for slow data gathering increases, we are going to learn more. We are going to find more disappearances, more appearances, more transients of every kind. We are going to discover slowly but surely the true nature of the dark spaces between the stars. So let me come back now to the puzzle I started with, the vanished stars on the photographic plates from 1952. What finally can we say about them? We can say, first, that some of them are probably artifacts, defects on the plates, cosmic rays, asteroid trails, plate scratches, the usual sources of false positives in any astronomical survey. Careful work has thrown out most of these candidates, but a few might still be hiding in the residual list. We can say, second, that some of them are probably massive stars that underwent failed supernovae. They collapsed directly into black holes with only a brief flash of light to mark their passing, and now we cannot see them. The Vasco team estimates that the rate of these events should be detectable with their methods, and the candidates they've identified are consistent with this picture. We can say, third, that some of them might be related to the kinds of unusual transient phenomena that we're only just beginning to understand. There are entire categories of stellar variability and stellar disappearance that we have catalogs for now, but that were unknown to astronomers in 1952. Some of the vanished objects might be brief flares that happen to be captured at maximum brightness and have since faded below detection. Some might be ordinary variable stars in unusual states. Some might be the result of stellar interactions we haven't fully modeled. And we can say, fourth, that some of them, and this is the truly intriguing part, the part that I find most evocative, some of them might be hints of something more exotic, of primordial black holes consuming small stars, of dark compact objects passing in front of distant suns, of phenomena that, when finally understood, will tell us something new and profound about the nature of the cosmos. We don't know which is which. We don't yet have the data to distinguish among the hypotheses, but we will. Within the next decade or two, with new sky surveys coming online and with the data from Gaia continuing to be analyzed, we are going to make progress on this question. We are going to find more disappearing stars, characterize them better, and figure out what's actually happening to them. The mystery, in other words, is not permanent. It is a temporary state of our knowledge, one that science is actively working to resolve. And while we're waiting for those answers, I want to leave you with one more thought. Because the story of the disappearing stars is, in a deep sense, a story about the limits of human observation. It is a story about how much we don't know, even about our immediate cosmic environment. It is a story about how, despite all our extraordinary scientific achievements, despite our space telescopes and our particle accelerators and our gravitational wave detectors, the universe still holds vast reservoirs of mystery. This should not, I want to insist, be a discouraging thought. It should be an exhilarating one, because the alternative, the universe in which we know everything, where every star is accounted for, where nothing surprising ever happens, that universe is not the one we actually live in. The universe we live in is a place where things vanish, where dark companions drift unseen, where new structures await discovery just beyond the limits of our current vision. It is, in short, a universe still full of things to discover. And for those of us who care about understanding the cosmos, that is the most precious thing imaginable. I think about William Herschel, looking through his telescope on a cold night in 18th century England, seeing a hole in the heavens and not knowing that what he was seeing was a cloud of dust hiding the stars behind it. He thought he was looking at an absence. He was actually looking at a presence. And his confusion, his honest misinterpretation of what he was seeing, was the beginning of a long process of discovery that has continued for 2.5 centuries and is still going on today. We are in a similar position now. When we look at the disappearing stars, we are seeing absences. We are seeing places where light used to be and isn't anymore. But behind those absences, somewhere, there are presences, there are causes, there are objects or processes or phenomena that we have not yet identified that explain what we're seeing. And the process of discovery, the process of figuring out what those presences actually are, is the great adventure of contemporary astrophysics. The stars are not really erasing themselves, of course. Stars don't do that. Something is erasing them from our perspective by various means, some of which we understand, some of which we don't. And the deepest, most profound implication of the Vasco project, of all the work being done on stellar disappearances, is that there is more to the universe than meets the eye. Quite literally, the dark spaces of the cosmos are not empty. They are full of structure, of dynamics, of objects and processes that we have only begun to map. And one of those things, perhaps, is moving toward us, or rather, we are moving toward it. We are on a journey through the galaxy, through the local bubble, through the patterns of cosmic dust and dark companions that surround us. And every step of that journey brings us closer to encounters we cannot yet anticipate, to discoveries we cannot yet predict, to truths about the universe that we will only learn once we get there. The cosmos, in this sense, is always coming closer to us, or we are always coming closer to it. The boundary keeps shifting, the frontier keeps moving, and the dark spaces, with their hidden contents, are not eternal mysteries to be feared, but ongoing puzzles to be explored. So the next time you look up at the night sky, the next time you find yourself somewhere dark enough to actually see the stars away from city lights on a clear, quiet night, I want you to remember a few things. I want you to remember that the sky you're seeing is not the same sky your ancestors saw, and it is not the same sky your descendants will see. I want you to remember that some of the lights you can see may not be there anymore, having been swallowed by black holes or hidden by dust, with their final photons still in transit to your eyes. I want you to remember that the dark spaces between the stars are not empty, but populated by invisible companions whose nature we are only just beginning to understand. And I want you to remember that, even on the timescale of a single human life, the universe is alive with change. Look at the brightest star you can see and ask yourself, will it be there in 100 years? Probably, almost certainly. Stars, on average, are stable for very long times, but maybe not. Maybe that particular star, the one you're looking at, is the one that won't be there. Maybe it's the next vanished star. Maybe its light is already on its way to disappearing from our view. We don't know. And that, I think, is the most beautiful part of the story. We don't know. We can't know. But we can ask. We can look. We can compare old plates to new images. And we can search for patterns. And we can theorize, and we can build new telescopes, and we can wait for new data, and we can keep doing the slow, patient work of science. The work that, over centuries, has expanded our knowledge from a tiny dot of awareness on a small planet to a sweeping vision of a cosmos billions of light years across. The stars are not erasing themselves. something is erasing them. And whatever that something is, we are going to find out. Maybe not in my lifetime, maybe not in yours, but eventually, because the universe rewards persistence, because nature always answers our questions, eventually, if we ask them carefully enough and patiently enough, and in the meantime, we have this remarkable gift, the gift of living in a moment when the questions are still open, the gift of being conscious beings on a planet, circling an ordinary star in an ordinary galaxy, capable of looking out into the cosmos and asking with all the curiosity our species has ever mustered, what's out there? What's happening? What's coming? The answers, when they come, will surprise us. They always do. The universe has been surprising us for as long as we've been paying attention. Every time we think we understand something, the cosmos reveals another layer of strangeness, another corner of mystery, another puzzle to solve. And the disappearing stars are, in this sense, just the latest in a long line of beautiful mysteries, the latest of a long line of invitations from the universe to keep looking, keep asking, keep wondering. So go outside tonight, look up, find the brightest stars and the dark patches between them, and know that behind the curtain of the everyday, the universe is busy, it is moving. It is, in its own slow, majestic way, coming closer to us, and we, in our own way, are coming closer to it. The sky is not just beautiful, it is alive. And it is, even now, even as we speak, telling us new things about what it is to exist in this extraordinary place we call the cosmos. Thank you for joining me on this journey. Until next time, keep looking up.